Hi, my name is Joe Simmons, and I will be representing the Fuchsia team. And the Fuchsia team is Mark Brewster and also Jonathan Wooten. Today I will be presenting the data collected for the steady state and the unit step experiments for the pressure control system. Damper 2 closed, to be specific. For an overview of the presentation, we will be talking about the input and output for the steady state and unit step diagrams that my team collected. I will also be presenting the calculated analysis for each of the diagrams and what they represent. For the background information about our laboratory, in the engine assembly plant in Dunlap, Tennessee is a spray booth station controlled by 2 dampers. The spray booths are controlled by an input from a motor blower, and an output is the pressure measured in centimeters of water. For our laboratory, we ran the trials with a damper 2 close and collected our data accordingly. The way the laboratory was ran was with a remote system controlled by an input program from a remote PC. The input power percentage represented by the function MT, and the output was measured in centimeters of water represented by the function CT. The data sent from the system was stored in table files, which was opened by programs such as Microsoft Excel. Here's one example of our steady state input diagram given for the pressure system. The input shown in by the blue line is a constant input provided to the system at 80%, and the red line is the output from the system. As you can see, the steady state was achieved after 1 second of runtime. The average data from this experiment was 45.9 with a tolerance of 1.6 centimeters of water. This trial was ran over a course of 30 seconds. This diagram is collected data for one of my team's trials, or all of the team's trials, sorry. As you can see from the trend line, the linear curve was achieved between 20% and 90%. The other input values were omitted because they skewed off the chart so much. For the steady state analysis, we estimated 0.7 centimeters of water increase for every 1% of input to the system. In the next diagram, we examined the unit step in both directions, up and down. In each of these controlled trials, we examined our delta M, delta C, and our gain, represented by the variable K. Delta M is a step in either the positive or negative direction. Delta C is the step of the output measured by centimeters of water. The gain is calculated by dividing delta C by delta M. In this example, we found our gain to be 55% for initial value of 5% of power and a delta M of 40%. From the unit step diagrams, we were able to find the average of a gain, dead time, and average response times for our data. For the collected data for percentage gain, we looked at all of our trials and presented the average of what we saw. Each member was responsible for a region of the given range. Mark was the lower range, Jonathan calculated the middle, and I had the upper range. From the data collected, we saw varying data based on range position. The range increased, so did the gain. As you can see from the step down to the step down middle to the step down upper, it increased, and also from the step lower, step up middle, and step up upper. Similar to our analysis, we saw the dead time of our data change based on the range defined and also the direction of data collected. For our time constant, we saw fluctuating averages for our data ranging from 0.13 to 0.2 statistically. This was our step time tau. For our trials, we focused on the data collected while damper 2 was closed, and we collected our data accordingly. We were able to define the percentage gain, dead time, and time constant for all the unit step diagrams, and also the linear representation for the steady state diagram. Thank you.